is a lecture 2 from me. In last session, we introduced the energy equations as knows the difference between Bernoulli equation and the real energy equation. In fact, same for ideal case. If we don't consider friction loss, energy loss due to friction in the fluid, in the pipeline, then it is Bernoulli equation. But for real situation, we have to consider friction loss. And it is energy equation. We'll do more exercises because this is one of the main focus of my lecture. We have to use the energy equation for different pipeline flow, including air duct and especially water flow pipeline. Because as building service engineer in the future, you have to design pipelines, especially for air conditioning. In air conditioning, we have chilled water pipeline, fresh water pipeline, hot water pipeline, especially air duct as well. So this topic is very important. Now, I would like to introduce another related topic, flow measurements. I understand Professor Tang has introduced some basic instrument like I think Orifice, maybe another measurement instrument. I think I will introduce the details, and at the same time, I'll introduce other instruments, so you understand whole picture of flow measurements. You see, most of the flow measurements is based on this principle. It means to narrow the path of water or air, narrow it. You see, smaller opening to add orifice or other instrument so that it's narrowed. The path is narrowed. Then what happens? The velocity here is much faster. The velocity here and the velocity here is much faster. Here it is called Venturi contractor. So the narrowest position for this flow. Why it is when the velocity is slow, what happens? The pressure here, static pressure. The velocity is high, the static pressure is very low. And the static pressure is high. So we can measure the pressure difference between these 2 points, and then we can find flow rate. So this is a flow rate. For different instruments, we have different principles, and then we have different equations. What is a flow rate? We have 2 flow rates. One is called m dot, that is mass flow rate. Mass flow rate unit is kilogram per second, or per hour, or per minute. So this one is volumetric flow rate, as it is cubic meter per second, or per hour, or per minute. Usually we use SI unit per second. Sometimes you may say per hour, per minute. And this is a typical equation first. We need to understand this one. Volumetric flow rate is equal to velocity times the cross-section area. For any area, if we know the cross-section area, we know the velocity, and then we know the flow rate. So sometimes we measure the velocity, and then we know the section area, and we can calculate the flow rate. Or if we know the flow rate, we can calculate velocity, the mean velocity, average velocity. So the velocity unit is meter per second. And times area unit is meter squared. So the final unit is, sorry, not meter per second. Meter, yeah, the final unit is cubic meter per second, correct? Yeah, per second. Cubic meter per second. So whenever you do exercise of thermodynamic or for heady thermal flows, try to write down unit, because the unit can help you to identify if something wrong or not. If the unit is wrong, then the calculation is wrong. But if the unit is correct, it doesn't mean that your calculation is correct. So try to write down the unit. For the final examination or the test, if you write the full unit, you may get full mark. But if you don't write any a unit, I will definitely deduct some mark for you. So unit is very important for fundamental engineering subject, heat transfer, thermodynamics, and so on. What method can we use to measure water flow rate? Because water flow rate, not just water, air flow rate, gas flow rate, steam flow rate, very important for building service engineering. Because we need to know the flow rate or velocity, and then we can determine the amount of load and so on, the pipeline diameter, and so on. There are many types, I must say, instruments for measuring liquid or gas flow rate or flow velocity. And the accuracy of flow rate, flow measurement vary from instrument to instrument, and the desired accuracy will vary from application to application. So that's why I want to give you a full picture to introduce most of the available instrument or flow rate measurement, so that you can choose the right method to measure your flow rate in the future. Measuring flow rate is one of the most important aspects of process control. It's very, very important for building service engineer. You must know the flow rate of chilled water. Then you can determine the pipeline diameter and the cooling, if you know the cooling load. Then, especially when you do design and performance analysis, flow rate is one of the most important parameters. It is one of the most frequently measured process variable. Yes, we need to measure flow rate wherever we do lab tests of air conditioning system, not just air conditioning. Fresh water supply. Now we are working for WSD, Water Supply Department, WSD in Hong Kong, to develop water turbine for power generation from pipeline. Every day, nearly every day, we have to measure flow rate. So very important. That's why I need to introduce available flow rates instrument, measurement flow rate instrument. Flow tends to be the most difficult variable to measure. You must understand, it's easy to measure temperature. It's easy to measure, say, relative humidity and wind velocity, but pressure as well. Flow pipeline pressure is very easy to measure pressure, temperature, but it's not easy to measure flow rate. The accuracy measurement accuracy of flow rate is not as good as the measurement of temperature and velocity, and especially temperature and pressure of pipeline, water pipeline. So that's why it's one of the most difficult variable to measure. No single flow meter can cover all flow application. So that's why we need to choose most available instrument for flow rate measurement. Then you can choose the right one. For example, if you want to measure airflow in your room or outside, of course, you should not choose any orifice, and you should choose thermal instrument. I'll introduce both of them to you later. And what affects the measurement flow? Physical properties affecting fluid's flow. First, the velocity of fluid is defined as the fluid speed in the direction of flow. Velocity, meter, you have to know that, meter per second. Meter per second. Fluid velocity depends on the head pressure that is forcing the fluid through the pipeline. Greater the pressure, head pressure, faster the flow rate. And pipe size. Larger pipe size, the greater the potential flow rate. Smaller pipeline, of course, more friction. More friction. That's why slower flow rate. So pipeline very important. Pipeline size. Pipe friction. Reduce the flow rate through the pipeline. So that's why we need to calculate the relative roughness. If too rough, the inner surface of the pipeline, it will increase flow resistance. So flow rate of the fluid is slower near wall of pipe than center. Yes, because of the friction between fluid and the inner wall of the pipeline. Same as I mentioned in the river. If you want to go upwards and in a shape, and shape tend to go near the bank, near the shore, because the flow is slower, then the friction is slower, is less. But if you want to go, for example, this is a river, and the flow rate, the velocity is very high here. If you want to go upwards, of course, the shape will tend to go this way, near the bank, because the velocity here is slow. Why do we have a very slow velocity? Because of friction between the bank and the water. So, another one, fluid viscosity. I show the two fluid viscosities last session. What are they called? A dynamic viscosity and divide by, and then if divide by density, then it's kinematic viscosity. To know the relationship, usually we use dynamic viscosity. It's physical resistant to flow. Higher velocity means slower flow rate. Sticky, like it's very, very sticky than higher viscosity. Like oil pipeline, for example, China import a lot of oil from Russia. The pipeline may be 1,000 kilometers, and it's very sticky. Viscosity is very high for oil. And how to transport in a pipeline, oil pipeline? Then we have to heat to reduce the viscosity. When the temperature is higher, the viscosity is lower. So, say after a few kilometers, then a boiler must be used to heat the pipeline, so that viscosity is less. Another parameter is specific gravity of the fluid. This is constant. At any given operation condition, higher the fluid's specific gravity, lower the fluid flow rate. Specific gravity means the gravity divided by mass. The fluid condition. The condition of fluid, clean or not, or dirty, also limit the flow measurement. Sometimes it cause blockade, target, eroded, dirty fluids are used. So it depends. For building service engineering, usually we just measure very clean, chilled water, fresh water, air in air conditioning system. So no such problem. But if you want to measure some dirty flows, then we must be careful. We have to choose some magnetic measurement so our accuracy is better and our instrument is not damaged. Velocity profile have major effect on the accuracy of performance. Later we introduce some of these 3 examples. For flow rate measurement, in building service engineering, usually a pipeline, first water pipeline, for example, usually we use these 3 measurement instruments. Of course, I will also introduce other instruments as well later today. But you have to understand all the principles of these 3 measurements. A similar principle, similar equations, but there are different test measurement. So try to understand the details. If you have any questions, it must be related to these 3 meters. The first one is Orifice meters, Venturi meter, flow nozzle. See, Orifice, similar principle. We have a smaller opening here. You see, if we want to measure the flow rate of this pipeline, we simply cut it, and then we add 2 flange here, flange, 2 flange, 1, 2, and then insert an orifice here. And in the center, there is an opening, and water will go through this opening. Then we measure the velocity here, the pressure here and the pressure here, static pressures. And we can derive the equation to calculate the flow rate. That's the main principle. Later I'll show you how to calculate the flow rate. Similar for Venturi meter. You see, similar. Narrow it. Remember, narrow it. We must narrow it. Let the flow speed higher and the pressure is lower. And how to do it? Narrow the path, similar like this orifice or Venturi meter. So this is a narrowed part. And we measure the pressure between the inlet and the narrowed part, and we measure the pressure difference. And of course, we must know the area, cross-section area, or diameter, or radius, and we can calculate the flow rate. We'll derive these 2 equations as well. Similar for these flow nozzles. Here we have a flow nozzle, and then measure the pressure difference as well. See, also narrowed path. Similar principle, I must say. And let's start from a nozzle, because the principles are the same. We can use this equation for other measurement data. This is a common one. Say, sorry, there's something wrong with this. Is it M1? Is it M1? M2? Is it 01, A1, B1? Okay. Now we have to use knowledge equation here. Why don't we use energy equation? I mentioned that if we don't consider friction, then it is Bernoulli's equation. Similar. And we also need to use a continuity equation. For fluid dynamics, I think Professor Pang has introduced that we have 3 main equations. Energy equation, that's a Bernoulli's equation. continuity equation, and another equation is called momentum equation. In Chinese, you know, energy Bernoulli's equation, energy equation, 能量方程. Continuity equation means 连续方程. Bernoulli, momentum equation is 动量方程. You should understand these three equations, especially continuity equation, Bernoulli's equation. Okay, and what is a continuity equation? For any two section, we assume that any section, the flow rate is the same. Why? The flow rate means m cubic meter per second or per hour or per minute, because we assume that it's constant flow, static flow. Otherwise, the velocity and the flow rate change with time. But for building surface engineering system, usually flow rate is constant. The mass flow rate also constant, of course, because the mass cannot be destroyed or created. As mass conservation. Energy, same. Energy for the first law of thermodynamics, energy cannot be destroyed or created. So that's why we have the Bernoulli's equation, energy equation. Now is continuity equation. M1 is equal to M2. M1 here, this position, M2 is here, N1, N2. And M is density rho times AV. M means kilogram per, M means kilogram per second. M, kilogram per second. How about this? This is rho means density as a kilogram per cubic meter, and area is cubic meter, right? The center square meter. Sorry, V means meter per second. Meter per second. So it means square meter, meter, cubic meter deleted, and it is kilogram per second. So that's why, remember, the velocity, mass velocity is always equal to rho AV. V means velocity, rho means density, A is cross-section area. Then mass at point 1 here is rho A1 V1 velocity. Velocity means the mean velocity, not a velocity at any point. It's a mean velocity, remember? I introduced that in the last session. Mean velocity. Mean. Okay. Then it's equal to the mass velocity here. Rho 2 A2 V2 density. For water, you can assume that the density is always 1,000 kilogram per cubic meter for water. For other fluids, different. Air is only 1.2 kilogram per cubic meter. So it depends. You know the cross-section area. You need to know the diameter first, I think. So this is a continuity equation. Because the density is the same, and we delete it here, and you have A1V1 equals A2V2. And if you know, usually the two diameters are known. If you know one velocity, you know another velocity. The velocity here, pressure can be measured here. Pressure here, pressure the same. Static pressure, not kinetic energy pressure. Static pressure. So we have this continuity equation. Most of the cases, pipeline flow, you need to write the continuity equation first, and write the energy equation, say energy equation, Bernoulli's equation. What is the principle of Bernoulli's equation? Say total pressure or total energy must be constant. And for any steady, incompressible fluid, the fluid is not compressible. So the density is the same. Steady state, no change with time. The total pressures are the same, or the total energy must be the same. The total energy at this position, the total energy at this position must be the same. Let's say, what are the total pressure or total energy here? In fact, sometimes they are not pressure. Just think that it can be represented by pressure. The first one is pressure, static pressure. And the second one is kinetic energy. The third one is potential energy. So for thermal fluid study, you should know for any movement of a body, there are three energies: internal energy, kinetic energy, and potential energy. For internal energy, here we use this P to represent it for fluid flow because no temperature is considered. If we want to consider temperature like thermodynamic, and we have to include the internal energy, U. But here, we don't consider temperature, and we don't consider other internal energy. Only the P, the pressure, static pressure. Higher pressure, if you have a container, higher pressure container, then something wrong, an explosion. Higher pressure means more serious explosion. That's internal energy. And another energy called kinetic energy. I explained this last time. For example, a car, a very high speed car traveling and suddenly crash onto a wall. If the speed is very high, it means very serious crash. As it's very slow, then no damage maybe. So don't drive too fast in the future. It's kinetic energy. High velocity means much more kinetic energy. You see, it's squared. And another one is potential energy, rho GH. You must learn from Professor Tang. Any potential energy is calculated by rho GH. Rho GH. G means gravitational force 10.81. This is a height. This is density. I give you an example of the Yangtze River in China. In Wuhan, near Wuhan, Yangtze River, or the Three Gorges Dam is very high, 180 meter. The water level could be 170 meter, 75 meter, or 165 meter, very high. Why? Because Z is very high and very high potential energy. So more electricity can be generated from the dam. So that's why higher dam, more energy. So that is potential energy. Similar, if you drop something from higher position, more damage. So that is so-called potential energy. So that's why we assume that they are called energy. And internal energy, kinetic energy, tension energy, similar like other energy equations. But here we don't consider the friction loss. That's why we call it Bernoulli equation. And for position 1 and position 2, you see we can write this total pressure at the entrance and total pressure at outlet of the nozzle. Remember, this is a nozzle. Narrowed path, only this. diameter. So diameter is the cross-section area is given, or diameter is given. And P1 plus the kinetic energy at position 1, the potential energy at position 2 must be equal to the total pressures at position 2. Remember, this position. We measure the static pressure here. Same. So P means static pressure. This is total pressure. This is dynamic pressure, or usually we call it kinetic energy or kinetic pressure. It's a potential pressure or potential energy. And we can simplify this too. If this is a horizontal position, and Z must be the same. What is Z? Z means we give a datum. You know the datum? Refer any datum? D-A-T-U T-O-M. And this distance is called Z. And Z1 and Z2 must be the same for horizontal one. But even the inclined one, because they are very close, we assume that they are the same. So we can delete these two components because they are the same. See, the pressure is different because the velocity is different. We have different velocity, definitely, because it's a narrowed path. And the velocity here is much higher than the velocity here. And the pressure must be much lower. So that is a Bernoulli's equation. You know, there is a story. If you travel in the sea or river, to both usually not close to each other, because if you see, I show you these two figure, these two piece of paper. If you blow it, what happens? It will not go apart, but very, very. You see why? Because why? Because the velocity is higher here and the pressure is lower. And the higher pressure outside, you push this towards. What happens? The two poles traveling in the river, in the sea, not close to each other, otherwise they crash because the smaller pressure between the poles. Similar like aircraft, same. Or lift as well. Every day you take lift in Hong Kong, you will see, you may feel some the lower pressure on your ear. Why? Because the velocity is high. Velocity is high, the pressure is low. That's Bernoulli's equation, one of the applications. And flows through a nozzle. And how to calculate it? Say, and the pressure difference is equal to P1 over minus P2 here. Say this Bernoulli's equation. What is the pressure difference? P1 minus P2 must be equal to, because it's deleted, and it must be equal to the kinetic energy at position 2 minus the kinetic energy at position 1. That's why we have this equation. The pressure difference between these 2 points, are they similar? 2 points must be equal to the kinetic energy at this point minus the kinetic energy pressure at this point. So that we can use the two velocity to represent pressure difference. And the velocity can be something wrong. And we use the pressure. Okay. Yeah. A1 V1 will be equal to A2 V2. A means area, V means velocity. Then we use this equation to change, because we want to know the velocity here, V1, but we don't know the velocity here. We cannot measure the velocity here. We don't need to measure the velocity here, but we want to know the velocity here. That's why we need to do measurement, mean velocity. So replace V2 by V1. How to replace it? Because A2 V2 must be equal to VA1 times V. So we can use this two. We can replace V2 by V1. That's why we have the ratio of the two area, cross-section area. The two cross-section area can also be represented by what? Diameter squared ratio. 1/2 diameter of the two squared, because it's equal to pi d squared. No, not pi d squared, divided by 4. Same. So we can use the area ratio to represent velocity ratio and times V1 squared. And V1 the same. V1 squared is the same. And we can derive the equation like this. And this part unknown. A1 is known, A2 is known, because we know the diameter. So the area unknown. And it means the density is known, 1000 for water, 1.2 for air. And if we know the pressure difference, we can calculate velocity. All right? The velocity, the density is the same. I must say the two densities are the same. So that's why we have this simple equation. And we can find V1. All right? Represented by the pressure difference. And we simply just need to measure the pressure difference here by using this U-tube pressure. I think, sorry. So, Professor Tang has introduced this U-tube pressure difference measurement. U-tube. How to measure the pressure difference here? Say we simply drill a hole here, another hole here, then connect a U-tube. In the U-tube, there is another liquid. Usually it's heavier than the measured fluid. If the fluid is water, then usually we use mercury. Water's density is 1000, correct? Water's density is 1000 kilogram per cubic meter. How about mercury density? 13 times. I couldn't remember the details. 13 times 136, I couldn't remember. 13 times the density of water. That's why it's very heavy. If you put mercury in the water, definitely at the bottom. So that's why we use mercury here. If you measure air velocity, of course, don't use mercury. Otherwise, the two level will be very, very small. If you measure air velocity, air flow rate, usually we use water for the measurement of fluid. And because the pressure here is higher than the pressure here, velocity here is lower. And says it will push the mercury level down and the mercury level here up. That's why we can measure the pressure difference, delta P. And if we know the pressure difference here, then we can find the velocity at this point. So this is a principle of velocity measurement. If we know the velocity V1, and it's easy to find flow rate times A1 is equal to what? Q1. Q1. If we know the Q1, then we can know that's a volumetric flow rate. And we can calculate the mass flow rate. Just simply times, correct? U V1 A1 A. The mass flow rate is rho Q, correct? Because it's a kilogram per cubic meter. It's a cubic meter per second. Yeah. So that is kilogram per second, correct? And we can calculate the mass flow rate. To measure the velocity first, and then the flow rate. That's why we have this equation. V1, velocity at point 1 equal to the delta P, the pressure difference, 2 times the pressure difference. This is from this equation. And take rho, if you remember, this is rho, and divide by this combination of cross-section areas. And the flow rate is given by this, A1 V1, same, just simply times A1. And you may say, so this is the equation, similar like this, is exactly the same. And you may say, if this is correct, because we neglect the friction loss. It must be friction loss. Anyway, orifice, that must be friction loss. And there must be friction loss here as well. If you have narrowed paths, the friction loss is very serious. Even though it's very, very smooth, and we still have friction loss. And for this not smooth, sharp edge, and definitely have friction loss. And how to consider friction loss so that the measurement is accurate? And we simply add a factor. Or you can say sometimes we call discharge coefficient, because it's a discharge. Flow rate is also called discharge. And CD means discharge coefficient. It's less than 1. If it is 1, then we neglect the flow rate. The flow rate will be smaller because of the friction. Say, it's a function of Reynolds number, native spec flow meter, most of definitely less than 1, not 1. 0.8, 0.9, or even 0.95 depends on the accuracy and the quality of the instrument. So we add a 1 to correct the accuracy. Otherwise, if it is 1, then we assume no friction. It's not true. And your measurement will be bigger than real flow rate. So this is always less than 1. So check out the flow measurement instrument. The manufacturer will provide a coefficient for you. If you buy flow meter, and they will give you coefficient. This coefficient is obtained in the manufacturer's laboratory and due to calibration. After they finish the manufacture of the instrument, then they will give to the laboratory to do the test. Of course, they have to measure the real flow rate by another more accurate instrument. Then compare the two measurement results, then to find this correction factor. You can call it correction factor. Then we call discharge coefficient. And to correct calculation, because of the neglect the friction loss. You know this basic principle. Similar like other measurement instrument, flow always give you a friction factor, discharge factor or discharge coefficient. Similar. And let's introduce the formal name. The first one is Venturi Meter. Say similar because it's similar, always narrowed path. And we can simply use the previous equation. N times this CD, discharge coefficient. But there is here, just like an orifice. Here is a gradual reduction of diameter of the path, so that we measure the pressure difference at this point and the pressure at this point by using U-tube, or you can connect a U-tube in this way. But if you just connect the two open, this is open to the environment. If the pressure is not very high, then the level here represent the static pressure at this point. The level here represents the static pressure at this point. And the level difference can be used to represent the pressure. So say, for most of the Venturi meter, the discharge coefficient is usually very high. See, 0.95 to 0.98. Why is very high? Because this is smooth, so that the friction loss is not very serious. Advantage, you see, pressure recovery, and pressure is recovered soon. We just insert this Venturi meter in the pipeline, and you can measure the pressure difference, and you can calculate flow rate after considering this discharge coefficient. Little power consumption. This little power consumption means of the electrical power is a resistance due to friction, because it's narrowed path. That's why there is resistance loss, energy loss due to resistance, but little. That's why the discharge coefficient is much higher. And this is real Venturi meter. You can see this is a inlet diameter. This is a narrowed diameter neck. We call neck. Then there is an opening here to connect pressure difference meter. But there are different kind of pressure difference measurement. And you see this angle is only 15 degrees. This angle is 21 degrees. And the Reynolds number can be calculated by this equation. Remember, this is a very popular property of fluid, because we need this property to find if the flow is turbulent or laminar. And we need this figure to find the friction factor of pipeline flow. friction factor F from Moody diagram if the flow is turbulent flow. So always calculate the Reynolds number to determine if the flow is turbulent or laminar. If the Reynolds number is less than 2,300, I think so, and we say it is turbulent, it's a laminar flow. If it is greater than 2,300, it is turbulent flow. So you should understand it. So here is kinetic viscosity, here is density, diameter, and velocity. And for different Reynolds number flow, higher means higher velocity, more turbulent, and better. Why? Why the discharge coefficient is close to 1, close to 0.98. So if we use this instrument to measure velocity, flow rate, velocity, the Reynolds number should be higher. Understand me? Otherwise, the accuracy is not good. So for different kind of Venturi meter, check requirement of Reynolds number for measurement. If your Reynolds number is smaller here, and you see the CD discharge coefficient may be only 0.7, 0.8, so it's quite different. So try to check the requirement of the Venturi meter after you buy it, if you use it. So this based on the condition in the pipe approaching the meter. So try to calculate first and check the accuracy of the flow measurement instrument. And for another, see this, this pressure recovery. See, the flow is here, and the pressure you can see suddenly reduced. Why? Because the velocity is higher, and the pressure must be lower. According to the Bernoulli's equation, the total pressure must be the same, and we neglect the potential pressure difference, and the internal pressure, and the energy and the kinetic energy sum must be the same. Then if you have high velocity, the pressure will be lower, and the pressure will be recovered later, but still lower, right? Because of the friction. So the friction determines your accuracy of your measurement. At the same time, if you add a flow meter in a pipeline, usually you increase the friction. When you determine the pump for circulation, the pump may be redesigned, selected. So be careful when you measure the flow rate in the pipeline. Another instrument is called Nozzle Flowmeter. And shorter and cheaper than Venturi, but larger pressure drop. I have shown you what is a nozzle. It's like this. Like this. It's a nozzle. So this is water flow. Narrowed path, larger pressure drop. Because Venturi meter can be made in smooth graduate transition. But here it's not. So that's why larger pressure drop and more power loss in operating. See, this is a Reynolds number, and 1,000 here. 2,000, 1,000, 2,000, 300, 3,000, 100,000. And you can see the discharge coefficient approach to 0.98 when the Reynolds number is 100,000. So that's why the pressure may not be covered. So that's why you must consider friction loss. So this is a flow measurement by an orifice. What's the difference? You see, this something we call this an. You see, this is a nozzle. You see, this is a nozzle. This is a nozzle. This is orifice. This is orifice. This is a nozzle. It's like this. But here, it's a vertical one. So this is a nozzle. This is an orifice. But similar principle. We need to measure pressure difference, and then use the equation to calculate the velocity of discharge or the flow rate. For the orifice, see, we measure. You see, the actual narrowed path is here. It's called Venturi contractor. Smaller than this diameter, smaller because of the momentum energy. But we don't know the diameter. So usually we use this diameter and then to calculate the area, and we use the discharge coefficient or another coefficient to correct the final result. Let's have a short break, 5 minutes short break, and we'll continue. If you have any question, you can type it in the chat function. Through the chat function, I will answer your questions later. Have a break, 5 minutes break. Okay, let's continue. Say we have just introduced the Venturi meter. The basic principle is very simple. Okay, you know the two diameter, then the entrance path and the net path, then you use the derived equation and consider discharge coefficient. Then you can calculate volumetric flow rate. And times SD, you can measure the mass flow rate. So you should be very, very familiar with this procedure. Now, let's introduce the third one, orifice flow measurement at orifice meter, second one. So this is orifice. So this is the orifice. It's a nozzle, but the principle, like Venturi meter, similar. Just measure it, remember. And for orifice meter, you see, we know the two diameter, the diameter here, and we can use the similar equation. We give you have known before. See this equation. Remember this equation we have derived. But here we add more coefficient. Unlike the Venturi meter, you can see we add other CV means coefficient of velocity. We correct the velocity at the beginning. Velocity. When you calculate the velocity, you use CV. You know the two pressure, head difference, kinetic energy at entrance. Easy to derive this. You use CV, coefficient of velocity. And CV is equal to A2 over A0. This is A0, cross-section area. This is A2. This is A2. The coefficient of contraction, CA. Sorry, C. Yes, CV. CC. Sorry. CV means the coefficient of velocity. CC means the coefficient of contraction. Here, we add another one, coefficient of contraction, and here we also add also have CD here. CD means CV times CC, the coefficient of velocity times the coefficient of contraction, SC. So similar. We use this equation. But here we add a CD here, CD squared here, to correct to different area ratio. So and its only difference is this. Only difference because it's very close to 1, so no much influence. But here is different. CD. So we need to consider CD here. So that is a flow through an orifice meter, similar. You can neglect this, but you still use this CD. Different manufacturer of measurement flow, the meter, give you different coefficient. Usually, we can neglect this. It's very close to 1. You can see the pressure at the beginning is like this and gradually lower because high velocity and then recovered. But friction loss is very, very serious because very narrowed path. And flow through an orifice meter, we can still use this equation, say exact same equation We measure the pressure difference at 2 points. Then we know the two area. And then we know the coefficient of discharge, or discharge coefficient. Similar, exact same equation. Advantage is that it's cheaper, cheapest, simplest, but biggest pressure drop, friction and the friction loss, and the power loss. That's why the discharge coefficient is much smaller. 0.6 compared with 0.95 for the Venturi meter. So that's why the pressure drop is serious and the power loss is very. So that's to be I should say not very accurate, but it's very simple. You simply put it inside and measure the pressure difference to find the flow rate. The pressure drop is caused by friction and turbulence of shear layer downstream of under contractor. Yeah, because of narrow flow here, the turbulence. And if we assume this is a ratio, this ratio is called times C is called Cm, and you can see it's a M, and you can see 0.85. This is the diameter ratio. The narrow diameter divided by normal diameter. Too narrow is here. For different Reynolds number, you can see the coefficient is very, very small here. So that's why this ratio should not be very big. If 0.8, then it's close to 0.9. So that's why we say not very accurate. Sometimes, if we simply want to estimate the flow rate, then we use this simpler and simpler measurement instrument. It's very easy. Another, I think Professor Tom may introduce this principle. Here I tell you how to do measurement, how to use this so-called pitot static tube. In Chinese called pitot tube. You may have used it in a lab, SE lab, to measure velocity. It's called pitot. It's a name, scientist name. Pitot tube, who invented this instrument. It's a simple device that measures stagnation pressure. It's shown. What is stagnation pressure? This is a pipeline, any flow, not just pipeline. For example, this is a pipeline flow. This is a pipeline. And suddenly, we add this pitot tube. Pitot tube consists of one path like this, dark one path. Inside, of course, air. Then there is a shell here. It's not open, but here is open. Here is open. So a shell, the two parts are not connected. The double shell. A shell connects to the another end of the U-tube, a pressure difference measurement. We call differential pressure transducer, or a nozzle to measure the pressure difference at U-tube. So that you can use the U-tube to measure the static pressure from this point and the kinetic energy pressure at this point. Why? You see, when flow from this point, any water particle, air particle, suddenly here stops. Why? Because here no flow to this direction. No flow. Stop it. Otherwise, the air will go flow in this way. No flow. because we use this here like a U-tube. Inside there is mercury, heavy, to stop the flow. For example, we use a U-tube to measure flow. U-tube. Here must be heavy fluid so that it can stop the flow. So, as shown, fluid is brought to rest. Flow velocity towards this direction. At the mouth of the tube, it's just like a mouth opening. And this point is called stagnation point. You see, stagnation point. No flow, no movement. That's why it's called stagnation point. And we write the energy equation from this point to this point, the energy equation. P1 over 2G. Note this energy equation. The unit is M. Meter unit. All the components, the unit is meter. So try to be familiar with the energy equation. Or you can say it's Bernoulli's equation, similar. Because no friction is considered. It's energy divided by rho g. Sometimes you may say pressure divided by g only. And sometimes you may say only P, not divided by G or rho G. All of them are energy, but different units. So here, usually we use this form of Bernoulli's equation because it's simple. The unit is simple, meter. And then when we consider the potential energy in meter, it's very simple. Just consider the vertical height of the body or of the fluid. So here is P1 over rho g as the gravitational acceleration, and plus the kinetic energy U1 squared over 2g, and plus the potential energy. This is kinetic energy. This is potential energy. This is internal energy, I must say. Here, this is 1. And 2, P2 here, P2. P2. And P2, the kinetic energy at this point is 0. No movement. The potential energy. So, here we neglect the difference of the two potential energy. Remember, we are not neglecting the potential energy. We neglect the potential energy difference because they are the same. Don't say we neglect the potential energy. We simply neglect the potential energy difference of the 2 points because it's very, very close. It may be horizontal, maybe not, but very close. Usually horizontal. And this value must be 0 because it's stagnation, no flow, 0. And how about say P1 is stagnation pressure, and here is I think I used the wrong one. So this one should be P2. P1 here. P1 is here. P1 is here. I think something wrong here. Anyway, P1 here, P2 here. P2. Stagnation pressure. Later, let's say check it. U1 is 0. U1 is 0. Z1 and Z2 are the same, so that the equation is different. I think this is U1 is 0. U2 is 0. Let's check. Let's say U2 is 0. I will change the writing. So the U1 is here. We are talking about this point. the particle flows from this point to this point. That's why we say this is U2, this is U1. Same. So that, say, we have a particle here, U1, 1, here is 2. This is 1, this is 2, this is 1. And then we measure the stagnation pressure here. That's why we have this equation. U1, A2, this is something wrong. This should be P1. Which one is P1? This is P1. This is 2. And stagnation pressure is equal to. Let's see. I think here something may be wrong. If we neglect this, U1, U2 is 0, and the pressure difference, potential difference is different, and P2 should be equal to and different. So this stagnation pressure should be P2. Don't neglect. And this is V1, P1, P1 V1. And we can find the velocity from the pressure difference. Stagnation pressure is higher. You see, we can measure stagnation pressure here. See this stagnation pressure goes this way, and then push this mercury column upwards because the pressure here is higher. Why? Because of the kinetic energy. Just water flow and suddenly stops there. So we can use this. This is so-called pitot tube, pitot static pressure. There is a shell here. Inside the shell is to measure the static pressure at this point. But here is 1. I'll change the number. Sorry. And we can use this U-tube to measure the flow rate, the velocity, the pressure here, and the pressure here, the difference. This pressure is the static pressure. And this pressure is stagnation pressure. So the stagnation pressure is higher than the static pressure. If we know the pressure difference, divide by the density, and we can find, I think, no squared, something wrong here, because it takes road. I'll revise it and upload it again in this afternoon. So using this, you can see very small tube, but it's double the shell inside, 2 parts. Then we can measure the pressure difference, stagnant pressure and the stagnation pressure and the static pressure. Here is stagnation pressure. Here is static pressure. Or we use 1 unit. It's 2 different pressure meter. This is 2 different. But we can combine these 2 together for this pitot tube static pressure measurement. Here, stagnation pressure. Here is static pressure. And if we know the difference between stagnation pressure and static pressure divided by the density, then we can find this not squared. Then we can find the velocity. So this is the basic principle of pitot static pressure measurement tube, or called pitot static tube. It's just like this, like a finger, very small finger, or even smaller, but it's double shell inside. Now here, usually connect to a U-tube manometer, then we measure the pressure difference. But remember, here we're measuring 1 point's velocity, not the mean velocity, because this only measure 1 point in a say point only. But if you can measure different points, change the position, change it at different points, then it's not difficult to measure the mean velocity. How to do it? I'll show you how to do it. We have a tutorial example next week to show how to do it. For example, I show you. Yeah, let me see. Okay, let's see. For example, if we have a circular pipeline, and this is the center of the pipeline, this is a cross section, and we choose this point to measure it. Let's say we choose a depth 1 millimeter or 1 centimeter, and we measure the velocity here, and we know the circular length. This is a radius times pi. We know this circular length times this depth. This depth could be 1 meter, 1 millimeter, or 1 centimeter. And we can find this area. We know the velocity at this point, and times the area, we know the velocity, the volumetric flow rate of this section, correct? And measure another point, another section, measure another point, another section, and add all these sections together, the flow rate, all these sections together, and divide by the whole area. Then we get the average or the mean velocity. You understand my point? As this student will introduce the details of this measurement in the tutorial next week. Okay, try to ask questions in the tutorial through Blackboard, or try to go to the classroom to have face-to-face lecture tutorials. So we can use static tube to measure velocity and flow rate at each section, and then add all the flow rate in each section, and we can find the total flow rate and divide by the area, that's the average or mean velocity. Same. It is complicated. Not very accuracy. You must control the position of the tube. Then, to calculate the circular area depth of the section, or sometimes it's very easy. Simply add into the air duct, special air duct. Then you can measure pressure difference velocity. This is so-called static tube for velocity measurement. Then other flow meter. I mentioned that I want to introduce more flow meters, so you must understand the principle. But from now, you may not need to do the calculation. Just give you a principle. So for the examination or test, I only include the main 3 flow meters: Venturi meter, Orifice, including you see Orifice, nozzle, test and examination, Venturi meter, and nozzle, and Orifice meter, and finally pitot tube, a pitot static tube meter, 4 meter. But the previous 3 have the similar principle. So it's not complicated for this session. Now I want to introduce more flow meters. It's very easy to use it. I use most of this in a laboratory test when I do my PhD study. You see, this is one of them. Very, very simple, very useful. A lot of application in chemical engineering or even building service engineering, but mainly in laboratory. It is called rotometer or variable area flow meter or flowing flow meter. You see, there is a narrowed, you see, this is a pipeline. Then this is a pipeline. And at this narrowed tube, and there is a flow, see, float with light liquid inside. With color, red, for example. And you measure the position of the float. If air or water goes this way, and higher velocity means higher position of this float. Low velocity, the float will drop to this end. And the manufacturer will give you an equation. The manufacturer derived on next slide. And according to different position, it's very easy to check the flow rate is given. For example, cubic meter per second or liter per second. And it's very easy to find the flow rate. Higher velocity, after the flow is higher, would be here, then the velocity is here. So you can see there are scales here. Then there is a float here. There is lighter liquid gas inside. Depends what float. What flow you want to measure, water or air, and you choose the right floating meter. We call it floating meter. You call it rotometer. And this is a equation very easy to derive because only change of cross-section area. And you can find the flow rate, the mass flow rate here, according to the density of the flow and the density of the two different densities. Because here in the float, the density is different. For water measurement, the density is lighter and the water density. So you must. This is a calculation density. This is a real density of water or air and a coefficient. So you don't need to derive it, but it's easy. As I mentioned, for the final test and examination, we only consider the 4 flow meter. Also, Orifice, Venturi, and digital static tube, 4 flow meters. And others. These are turbine flow meters. These are at very small turbine in the past. We know air turbine, water turbine. It's easy to understand it. High velocity and the air turbine can run high velocity. No velocity to turn. So we measure the revolution of this turbine. Then we can determine the flow rate, velocity, average velocity, and the flow rate. So here, just like water meter, every month or in 3 months in Hong Kong, we pay the water bill or town gas bill. How to do it? They have a meter. Of course, they may for most of the water meter similar like this. There is a turbine inside, and then to drive the meter so that you know how many cubic meter water is used in that month, and you pay the bill. Similar. This is called turbine flow meter. Very accurate. Very this traditional one, but very accurate. But the float must be very clean and not corrosive, so that it can be used for a long time. For most of the town gas and water flow, water supply, we use this kind of meter. Very reliable. Another advanced meter called magnetic flow meter. Sometimes we don't want to cut the pipeline to insert orifice, Venturi meter, especially for existing pipeline. For example, this pipeline in Hong Kong. Sometimes you can see suddenly due to the damage, some pipeline very old, maybe 20, 70 years already, then the pipeline is damaged. Suddenly water goes up, and a lot of seawater and fresh water is wasted. So every year we waste, not just in Hong Kong, everywhere, big cities, we waste a lot of fresh water and seawater because of damage of pipeline. The water pressure is very high in Hong Kong because we have different levels in Hong Kong. The pressure could be 80 meter or 80 meter, very high pressure. That's why water level is very high, water column is very high. And for existing pipeline, if we don't want to cut it, damage the pipeline for water flow measurement, then it's easy to use magnetic flow meter. Simply put the two pieces, put on the pipeline, and you can measure the flow rate. But not very accurate, I must say. You must do some calculation, calibration. You see, for magnetic flow rate, this is a housing, and the electromagnetic coil here. You have to connect to the electricity, of course, to emit magnetic through the coil, and non-magnetic flow tube, and insulating inner and flange. Connect. This is a pipeline, and you can see the principle magnetic flow meter based upon Faraday's law of electricity. The fluid is conductor, light conductor, not like metal, copper, very light. So the fluid is conductor inside, no pure water. And we have a coil here we call it electrodes. This is a magnetic, and light, very, very small power or electricity can be generated through this magnet. It's correct. Through this coil, and then magnet, because water flow in the magnetic field. That's why power can be generated. Or this voltage is very, very small. But we can detect it. We can measure it. And we can measure the velocity here. The voltage here. Measure the voltage, although maybe millivolts, but it's very clear. And this is flux density, magnetic flux density given by the manufacturer. This is length of the conductor, also given by the manufacturer. So the voltage is proportional to the velocity of the conductor. So if we can measure the velocity, then we can find the velocity. So this is basic principle of magnetic flow meter. It's very popular, especially for measurement of water pipeline on the existing pipeline. If we don't want to cut it, and simply put two pieces together on the pipeline and measure velocity. Although it's not very accurate, but it's fine. The accuracy is fine. Also expensive. I must say, it is expensive. Another one is called laser Doppler velocimetry. Velocimetry. Laser Doppler velocimetry, LDV, very popular. Is to use laser. It's an advanced flow measurement, especially not for water, especially for air measurement, wind tunnel measurement, or for very large wind turbine. Most of you may have with Llama Island. We have very large wind turbine, 800-watt wind turbine. Height could be 60 meters high. Before installation of the wind turbine, we need to measure the velocity 6 meters above sea level, above land level. How to do it? We can use laser Doppler velocimetry meter, or LV. And Doppler is a scientist name. It's an optical technique to measure and to send two beams of laser. Then, if we want to measure velocity here, this point in the space, then the two beams will meet here. It's a laser meter. One laser meter uses two mirror splitter. Then we split one laser laser beam into two beams. And this ascending lens meet together and reflected to this photo detector. This is receiving lens. We can measure turbulence. That determines the velocity at this point. We have done a lot of such experiments in China for wind farm measurement because I'm working on wind turbines. We can measure the velocity at 60, 70, or even 90 meter high level. For building service engineering, and we can measure air duct velocity. We add a transparent pipeline here and send beam into any points. Then we can measure the velocity in the pipeline. This is very popular, not for air duct measurement, but it's very popular for wind tunnel measurement. We don't need to cut the air duct. We simply use two beams from a laser generator to measure velocity in a wind tunnel. But this instrument is very expensive. Could be 1 million Hong Kong dollar a set. Very expensive. Okay, it can be used to measure flow velocity at any desired point without distributing the flow. Okay, another one. Yeah, another one. Ultrasonic flow meter. Here, again, you don't need to cut pipeline. And simply add a transmitting element and receiving element on the pipeline, and then connect to the power and send signal or signal. Ultrasonic signal. Or like this, send ultrasonic signal and receive it, then higher velocity, and you have received different signal. Similar like this. For different velocity, you receive different signal. Because the flow will disturb the ultrasonic signal. So the average velocity V in the pipeline is proportional to the wave travel time difference and can be determined by this, where L is the distance between the transducer and K is the constant of the instrument. Then you measure the time difference, and you can estimate velocity. This is also called Doppler effect ultrasonic flow meter. And any others? Last one, I think. Okay, thermal, hot wire, hot film anemometer, anemometer, thermal anemometer. We call it, it is called 热电. 热电. Sometime, if you are going to do final year research project next year, maybe, then 2 years later, you may need to measure the indoor air velocity or outdoor air velocity. We can use thermal anemometer. What's the principle? See, very tiny sensor here, put in air, and because the airflow here is velocity, not static. If static, then you will find the velocity 0. Higher velocity here, and it will affect the heat. The meter will send signal here to heat it. And higher velocity means the cooling rate is high. And it will affect the resistance here. And the resistance will be measured as this circuit, as this meter. See? Involve electrically heated sensor. So this sensor is heated and utilize a thermal effect to measure flow velocity. It means high velocity and higher cooling rate of the heated sensor, and you can measure the change of the voltage or resistor. Then the thermal anemometer have extremely small sensors, and then it can be used to measure the instantaneous velocity at any point in the flow without pressure disturbing the flow, especially air duct and indoor space to measure air velocity at any point, or outdoor space. It's a very, very popular thermal anemometer. We don't need to derive any equation. it is manufactured by produced by manufacturer, and simply measure it. And nowadays you can find a displayed data, recorded data. I think this is all the flow rate measurement meter I introduced. How many? Maybe 8 or 9. I couldn't remember. All of them are popular. It depends what flow you want to measure. Really depends. If you want to measure air velocity, use the thermal hot wire. We call it hot wire. In Chinese called say hot wire 热线风速仪 hot wire anemometer 热线 hot wire. If you want to measure water flow rate in the existing pipeline, you can use ultrasonic flow meter or laser Doppler flow meter, magnetic flow meter. For small water pipeline, home water supply, on-gas supply, usually they use turbine flow meter, very reliable. For laboratory small flow measurement, not accurate measurement, you can use flotometer, or sometimes we call floating meter. And for building service engineering measurement, especially air duct, we can use pitot-static tube measurement. Or we can use Orifice, especially for water measurement, water flow measurement, nozzle measurement, and Venturi Meter measurement. It really depends on what you want to measure, what situation, and you choose the right meter to do the measurement. Okay, I think I have to finish today's lecture. I'll revise one slide. Something wrong with number 1, number 2. I upload it again soon today. Here, I think something wrong here. You see, no square. This is 1 or 2. I have to check it. Anyway, we'll have a tutorial next week for this section. And I'll give you homework. We have to do more exercise. Don't just wait until the test, examination. We have to do exercise. We usually will have two homework. So next week, I'll give you homework. I'll upload maybe this week, and next week I'll upload into the blackboard. Homework. Then you need to write the answer by yourself, solution by yourself, and submit it to me. How to submit it? Last time you submit by email. You can submit by email, or maybe we can create blackboard. Anyway, I'll tell you. And after 2 more weeks, we have another homework. So 2 homework to do more exercise. We don't count your grade marks, but we use it as reference. If you have marginal mark at the end, then we have to check your homework. Remember, it's useful. But mainly, main purpose is to do exercise. To do more exercise. Just like mathematics in your school study, do more exercise. Because you can see we have included a lot of mathematical equations here. And then at the end, we'll have a test and final examination. The examination has been scheduled on 16th December, 10 o'clock to 17th December, 10 o'clock, 1 day. You just need to spend 3 hours, 2 hours, maybe a little bit more, 4 hours to finish it. this is a take-home examination. I hope all of you can pass examination. Try to study hard from now. Okay, I'll see you next time, next session. If you have any questions, you can ask the tutor of the tutorials, my PhD student and the doctor. One of them is doctor, finished PhD. They are very they are experts in fluid dynamics. Okay, I'll see you next time. You can send email to me to ask questions. Or you can come to my office. Goodbye.